Thank you, Fernando. Thank you, Alessandro, for inviting me. A little weaker thanks for making this 2 hours. I've never given a talk for 2 hours, although there might be some people in the audience who can distinctly remember a talk that felt like it was longer than that. Let me tell you what I'm going to try to do, since I didn't quite know how to meet the requirement to do the details, and I had started doing some slides. I'm going to tell you the things that are of interest to me. These translators will turn out to be minimal surfaces in a, as many of you know, in a metric that's not Euclidean, and because of that, all the stuff that I know can be used. The part that's hard, at least hard for me, is the stuff that is not like minimal surfaces. It involves PDE, in which I am possibly the weakest person in the room. So when I try to explain that to you, some of it is, to me, very tricky. Some of it is new and not due to me. So forgive me if it's a bit of a mess. Okay. Let's go. So a translator is a hypersurface in Euclidean space such that moving in a particular direction, v, is mean curvature flow. What that means is that the mean curvature vector is, that minus sign, it should have been a minus there in the first line, is the normal component of the vector v. And we're going to assume that v is always the downward direction, so things will be flowing down. And this equation here is a central equation. So basically, there are things when they flow by mean curvature, they translate, and that means that the part of it that looks like it shouldn't translate is absorbed in a diffeomorphism on the surface. Okay. A simple example of a translator is a vertical hyperplane. Then you see that h is 0, which is true on a hyperplane. Oh, sorry. And the vertical vector is tangent to the hyperplane. No other hyperplanes are translators. That's also evident from that. Okay. So if you have a translator that's a graph of a function u from some domain in Rn, then this is the equation that it satisfies. It looks like the minimal surface equation with a gradient term stuck at the end. And we'll call such a surface a translating graph, and sometimes even refer to the graph by the name of the function. Okay. We'd like to know if it's possible to classify all complete translators. And I don't know if that's possible, but what I'm going to do today is classify all complete translating graphs. I'm going to do it in R3. In some sense, you can do most of it for hypersurfaces, but I'm going to assume that n equals 2 from now on. Okay, we'll assume we're translating in the vertical direction, downward, and writing it out in very classical notation. You see the minimal surface equation plus this gradient term. Okay. Let me give you the simplest example. Many of you know it, but I think I should start slowly and probably continue slowly. Okay. Let's let z equal log cosine x. And that's defined for x greater than minus pi over 2. Pi over 2. And let's look at the graph of that. So here's z, here's x. One sees a curve like this. you can check that that the curvature of this curve is cosine of x, and that if you compute it out, this satisfies the translation equation. It translates down. If I take this curve and look at u of xy equals log cosine x, what I'm doing is now taking something defined on a strip of width pi. So this will be my x. In this case, this will be my y, and it is a product surface. It's a cylinder. That is also a translator. It's extremely easy to check, and this one should have a picture of it. There it is. It's the tan one. So let's refer to that as the Grim Reaper cylinder, and let's refer to tan as yellow. Okay. Now that surface is a product surface. Its curvature is identically 0. You can tilt it around around the axis pointing up, and you get something that looks blue. And what happens when you do that is, well, you get something like this. And its name is tilted Grim Reaper. I guess that last sentence qualifies as going slow enough. This thing is translating in a tilted direction, which I'll call E theta. If you look at what happens here, the length of this is cosine theta. So what you want to do, this is translating in this direction with unit speed. If you want it to translate down with unit speed, you have to scale it. And what you want to do is look what happens for this one. For this tilted surface, you get this is equal to minus cosine theta times E3 perp. So if I scale, I don't change the angle, I don't change the projection, but I do change the mean curvature. And if I scale by cosine theta, the mean curvature goes like 1 over that. So when I rescale this thing, so if I take the surface and rescale it, I get something defined over a width that's pi over cosine theta. So now theta will run between 0 and pi over 2. Do I say anything about this on the next page? Yeah. So as theta goes from 0 to pi over 2, this strip of width pi becomes infinitely wide as you're tilting more and more. If you let theta go to pi over 2, you're stretching this thing out and tilting it up. It becomes a vertical plane. So you go from the Grim Reaper to a vertical plane. I could have tilted the other way, but rotation is not going to make any difference to the mean curvature. So I can get any angle between 0 and pi over 2, and I could rotate this thing in any direction so I can get it tilting in the other way with the same angle. And by doing this, I didn't change the curvature, so the curvature is still 0. OK. These examples couldn't be simpler. And it turns out these are almost all the examples. OK, so let me try to answer this question. Why are they interested? Well, they provide very simple examples of mean curvature flow. That's the first one. And they provide models for singularity in mean curvature flow. So if you, and now let me work for curves in a plane. If I have a curve like this flowing under mean curvature, and I always draw it the wrong way, I'll draw it this way. If I go to the point of maximum curvature as this thing is flowing and rescale in the limit, I'll get something that's flowing by translation, namely the Grim Reaper curve. So things that flow, mean curvature translators are models for singularities in mean curvature flow. The next one, you'll have to forgive me because I'm going to use the wrong words for this. This is an idea due to Ilmanen that many of you know that I can talk about, meaning my knowledge of it is a little bit thin. Let's say I have a curve in the plane. I'll call that gamma. And I want it to flow by mean curvature. Well, I could let it flow by, let's see. So I could try to look at this equation. I'll write this way. Minus E3 perp over lambda. Now, I want to solve for a graph that satisfies this. So when lambda equals 1, it's just what we were doing before. And when lambda goes to infinity, this is flowing really, 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 really quickly. I'm going to claim, and I'm going to show you reasons why you can find a solution in 3 space with 0 boundary values on gamma that flows for this lambda. And now I'm going to let lambda go to 0. So this is flowing faster and faster. So I have a series of surfaces here that are graphs. They're translators, so they're all solutions of this equation back and forth. I let lambda go to 0, and they're going to get steeper and steeper. And that flow has a limit. I don't understand this. Maybe some of you do. But the limit consists of surfaces that are cylinders over this. And so in that limit, you have cylinders as the limit flow for mean curvature flow with varying speeds, where the speed is blowing up. If you slice those cylinders, you get curves. And that is mean curvature flow for this curve. So the words elliptic regularization are used here. I've just repeated them. I don't know exactly why that's considered elliptic regularization. And for me, the most important thing is that these translators provide examples of minimal surfaces in a non-Euclidean metric. So let's see what my slide has to say here. OK, so let's say I take the Euclidean metric delta ij, and I multiply it times a positive function. And I call this metric g tilde. And I want to look at the area in that metric of some surface M. So that's the integral of f dA, where this is the standard metric induced on the surface. If I take a normal variation vector field, so I take a normal variation m of t with variation vector field x of t, then if I work out the change of this area, I get the integral of the gradient of f x minus f times x times the mean curvature. OK, so if I want minimality in this metric, I see that the gradient of f over f, normal part has to be the mean curvature. And now if I choose f equal minus x3, I get the equation that E3 perp, this is the vertical component, this is the unit vector in the vertical direction, that this equals h. So this simple calculation shows that in this metric, these translators are minimal surfaces, and vice versa. So what does that do for me? It does a lot for me because I know stuff about minimal surfaces. And the stuff I'm going to use is minimal surface prone. So here's a result of Felix and friends. That if you have an entire graph that's a translator, and it's rotationally symmetric, it's given by this function. And as you go farther and farther out, it gets more and more vertical, so it's asymptotically a cylinder. Other examples. There are examples that aren't graphs. We'll get to those later. Yeah.
I wouldn't claim that we found the solution. We were the only ones, we were the first ones that maybe computed this next order term. I think people before you very well.
And who were those people? Ilmanen? How come everybody gives you credit then?
I don't know.
Well, let's leave it at that. Maybe they're calling.
The author is calling.
They're calling, yeah. Well, I don't know who found this this one, but there are.
I think this one we stumbled upon.
Okay, there are rotational annuli. You stumbled upon it. You found it.
We needed variables.
Okay, all right. So these are. This one is not a graph. There's a relatively recent paper modeled on Costa surfaces and its extensions, and using gluing methods or desingularizations to get complete translating solitons with finite non-zero genus. And if I'm lucky, I'll survive long enough to tell you about new families of non-rotational annuli. Probably not. But also, what I will survive long enough is to tell you about new families inspired by classical minimal surfaces. Okay, so the eminence grise in this work and in this paper is Tom Ilmanen. And many years ago in an unpublished work, he found a complete translator that was a graph defined over a strip that was maximally symmetric. So let me. So here's a strip. I don't know how wide it is, but there's an axis here and an axis here of symmetry of the strip, and there are functions u of x, y, which are symmetric. Sorry. That are translators. They attain their maximum at the origin, and at that maximum, if you look at the Hessian, you can get any sum of numbers that adds to -1 for k between 0 and 1/2. if k equals 0, you're looking at the Grim Reaper cylinder, and for k equals a half, you're looking at the bowl soliton. In between, it wasn't clear what you were looking at. But I think it was known that it looks something like this. In other words, it has a maximum. You can specify at the top what the second fundamental form is. It slopes down one way, down the other way, and it goes down to minus infinity. It wasn't known what the widths of the defining strip were. It wasn't known the properties of the surface. So what I'm going to tell you today, or try to tell you today, is that if you take W bigger than pi, you get one of these things. I'll tell you later that it has positive, strictly positive Gauss curvature. And the only other ones are the ones you've seen before. If W is bigger than pi, you have a tilted Grim Reaper of a specific tilt determined by W. And those are all the examples. So in particular, and I think I'll be using this fact later in the second hour if I survive, there is nothing over a thinner strip. There's nothing over a half plane. And there's the bowl soliton, which you get as a limit of the delta wings. Here, these Grim Reapers get steeper and steeper and steeper, and the limit, they're vertical planes. OK, so I know this is not supposed to be a presentation of sales talking about results, but if you don't take away anything else from this talk, that's the thing to remember. I'm going to try to tell you what the problems were and what the methods are. So let me tell you some other people who've worked in this. Thea Borney, is it Dan Lanford, and Giuseppe Tonali have given a different proof of the existence of delta wings, but not the uniqueness. They and we also got it got these existence proof in higher dimensions. I think the star of this presentation is Spruck and Zhao, who actually proved that complete translating graphs are convex. In other words, their curvature is non-negative. And Shirayari proved that the domain of a complete translating graph is a strip, a half plane, or the entire plane. I'll show you how to prove that. We were also able to do these results of Wang again. His proofs are hard to understand, that you don't get anything over a half plane, and that there's uniqueness for convex translating graphs that are entire. OK, so before starting off on proving this, let me tell you the techniques, what we get from this thing being minimal in that metric. So if you look at this metric, this first thing to notice is the metric is not complete. If you take a vertical curve, let's say something starting at the origin and going to infinity, the integral from 0 to infinity of e to the minus t dt, that's a curve that's divergent, but its length is finite. This metric also has non-positive curvature. We have not had a single use of that fact, but it bugs me that we don't. OK.
So you have been able to classify graphs up to the entire case?
What? We're going to classify entire graphs that are translators. Up to the entire?
Entire case you said that you need convexity.
I don't understand the question.
So what's your classification result for graphs?
Given an entire translating surface in R3 that is a graph. Sorry.
You mean a complete
Sorry, I misspoke. Giving a complete translating graph, it is either one of these delta wings or a tilted Grim Reaper. And the tilt could be 0, so it's the original Grim Reaper, period. What I did say is that the Zhao result about these things having non-negative curvature is critical for us.
So the bow salto is the only entire one.
It's the only entire one. Yeah. Yeah. And the reason for that is that it was known to be the only entire one if you assumed it had non-negative curvature. So that comes from Zhao.
Sorry, could you go back to the ninth?
Aye.
Yeah, because I think everything is there in some sense.
Where?
In the plot. Okay, the thing. So that the plus infinity sort of you have to the generations, right? So you have
Vertical plane, both.
Yeah.
Right.
Okay. Yeah.
We could stare at this for the next hour and a half.
no,
It's fine. Okay. Okay?
Yeah, great.
So I've talked about these previous results and useful results. I'm going to tell you how to get that Shirayari result and show you how the Zhao result is proved and tell you what the problems are. Okay. So is there any water? No? Okay. Too bad for me.
I'll get some.
Oh, you're going to miss the crucial part. Please, I would appreciate it. So look, if this thing is a minimal surface in a metric, the part of E3 pointing up is basically a normal vector field. It's non-negative on a graph. So that's a Jacobi field that's non-negative. So that means when you move these things up, you're going to have a family of stable minimal surfaces. These things translate up, and they're all minimal surfaces. So you get smooth subsequential convergence of complete translating graphs to complete translators. If I have a translator, then its vertical translators give a G minimal foliation, where G is this metric again. So M is in fact G area minimizing, and this gives local area estimates. Let me show you how that gives local area estimates. Okay. So I take some set here. There's all these surfaces moving up. So you take the domain of the graph, and then that domain cross R is foliated by these G minimal surfaces. Take one. I'll call it M. And take some compact set K and look at the boundary of K. This is area minimizing, so the area of M intersect K is equal to or less than 1/2 the area of the boundary of K. It's equal to or less than this area and this area. One of them is not greater than half of the area of the boundary. So you have local area estimates. So anything about smooth convergence that requires that, with the usual compactness theorems for minimal surfaces, is going to work. Okay. So let's do some preliminaries. So you have this Jacobi field E3n. N is the normal to your surface. And H, since it's a graph, we'll just assume that H is equal to or greater than 0. By abusive notation, I'm going to think of the mean curvature vector and the mean curvature quantity. They're different, but I'm going to use the same notation. All right. So suppose there's a point P on the surface where H of P equals 0. Well, that says that this term equals 0. you have a Jacobi field with a sign and 1, 0. So if it's equal to 0 at one place, it's equal to 0. It's equal to 0 everywhere. So then you have E3 dot n, the normal to the surface, is identically equal to 0. That says that E3 is tangent to the surface everywhere. That means that the surface looks like a curve gamma in R2 cross R. So M, the surface, is contained in gamma cross R. It's contained in a cylinder. What can gamma be? Well, the mean curvature now is identically equal to 0. So gamma is a line. So once you have mean curvature, that's a mean curvature of a graph with a sign, if it's 0 anywhere, you're looking at a piece of a vertical plane. So that means that if we're on a graph, and the graph is not a vertical plane, we can assume that h is greater than 0 everywhere. Okay, so the next thing I want to talk about is the Sprook. I want to mention is this Sprook-Zhao result. I'll be talking a fair amount about that soon, but I want to postpone the proof of that. That to me is hard, but it involves a method that we're going to see coming up over and over again in what we do. So I'm going to assume that result, and if the curvature equals 0 anywhere, then it's identically equal to 0. That's because, let me see if I get this right, K1 over H satisfies an elliptic equation, and I have K1 equal to greater than K2. Okay. And so this term is equal to or greater than 0. It equals 0 if and only if K1 equals 0. If K1 equals 0, then this thing is constant because it achieves its minimum. So that says the curvature is identically 0. So the curvature is identically 0. Let me try to tell you what that surface looks like. Remember talking about an entire, we're going to assume it's entire. So it's a ruled surface. Let's take a line along it. And the fact that K is identically 0 means that the normal along this line is constant. I can then take that line, see what its angle is with the xy plane. Pick out the Grim Reaper with lines with that angle. The normal is constant along that line. Along the Grim Reaper, you get angles that go through a semicircle. Pick the line that has a normal equal to the normal along this line. N equals a constant along L. So you have this line on the surface. The normal is constant to the surface along that line. You find a Grim Reaper that has that line parallel to it. You move it over, and you move the line on the Grim Reaper over to it that has that normal. Since the Grim Reaper goes from vertical to horizontal, you have an entire semicircle of those normals. You match them up along that line. Cauchy-Kovalevsky says they're the same. So the ones that are flat are tilted Grim Reapers or the Grim Reaper itself. Since I'm assuming I started out with this, I'm not going to get the plane. Okay. That was originally proved by Paco Martin, Savage, Hilejaj, and Smuch. If you're here, I don't know. I'm sorry for mispronouncing your name. Okay. Okay. So let's take a divergent surface. Let's take let me think for a minute.
There's some water there.
Oh, thank you.
Watch out.
Okay, so I have k equal to or greater than 0 everywhere along an example. So I take the examples that are not the tilted Grim Reaper. So I have k never 0, it's strictly greater than 0. I take a divergent, so if I look at this surface, since it's a graph, so I know I have k greater than 0 and entire graph. So here it is. It has some width w. I look at its Gauss map into the sphere. I choose the normal going up on this graph, so it goes into the hemisphere. This is a complete surface, so the Gauss map, the Gaussian image, is an open subset. Oh. Of a hemisphere. I now take a divergent sequence, pi. The pi's are going to infinity here. And I think of them on the graph. I've written them in the domain, but I think of them on the graph. And I pull the surface back by pi and take the height to the origin. I keep pulling back, What happens? I get a limit surface. I get some convergence. I use the minimal surface theory. I get smooth convergence to something. I have to worry about whether the limit is a vertical plane. I'm not going to worry about that. It is not. It's very, very simple to see that it isn't. But I get something converging on possibly a smaller strip. Its Gauss map is now going into the boundary. Let's call this subset O. It's going into the boundary of O. So I get a limit by pullbacks, pi going to infinity, of mi. And that's a surface I'll call M prime. Its Gauss map goes into the boundary of this open set. That has no measure. So I have a smooth surface. Its Gauss map goes into a set with no measure. Its curvature is 0. So that says asymptotically, as I pull back, I'm going to see a Grim Reaper or a tilted Grim Reaper. That says these things, when you start with k positive, are asymptotic to Grim Reapers. You can show that, we could show that when you go one way, you might get one Grim Reaper with this angle. You go the other way, you get a Grim Reaper with the other angle. So it does look a little like the picture of a delta wing that I showed you. But if I start out on something with W, how do I know that the Grim Reaper I get is the Grim Reaper defined on that width W? Imagine that I look at the cross sections So I'm now moving out. So I'll let x equal n. I have this strip coming through. I cut the surface. It looks like this. I'm going to draw that over here. This is the picture when I have n. I've taken these points, I've moved them down to the origin. The next one might look like this. So when I pull back in the limit, the width of the strip on which the limit is defined might be smaller. So you can't say which Grim Reaper it is. That's a big problem. I'm going to try to show you how to solve that problem. Because you'd like to say, if you have something on something of width w, when you take its asymptotic to the Grim Reaper, defined in that width, which tells you exactly the angle. Oh, sleep time. Okay. Okay. So this is actually a result of Spurk and Zhao in a paper that I admire greatly, posted about a year ago. First, they showed that you have the symmetry of this strip. You have horizontal symmetry. That's relatively easy when you have non-negative curvature. Then you can use the method of Alexandrov moving planes. But to show that the strip doesn't shrink in the limit, you have to do some work. So I lost it. I don't quite know what's happening here. I'm not getting motion.
Give it a second.
Yeah.
Seems like you might need to get back into full screen mode.
Am I not in full screen mode?
Apparently it's not.
Sorry.
No, I don't. That's not it. It's if you open up your presentation.
Thanks. Okay. So maybe after doing all that, well, I think I can do it on blackboards. Okay, so let's say u of xy is a translating graph. Then I'll look at this function v, which is defined to be e3.n, this function that comes up all the time, inverse. And I'll take eta to just be a simple affine function, alpha 0 plus alpha 1 x plus x1 plus alpha 2 x2. So it does not depend on the x3 direction. And the proposition I'd like to prove is this. eta times v cannot have a local max at a point where eta is positive. So if we have this graph u, then recall that the normal is just given by minus grad u 1 divided by the norm, by the square root rather of 1 plus grad u squared. So that means this function v, which is taking this normal and dotting it with n and then inverting it, is just the square root of 1 plus grad u squared. Okay, so let me do something. It's probably embarrassing for me to do this, but I want to do it to try to tell you how I think about things. And it had to do with some problem I had with the notion of the drift Laplacian. So if I take Laplacian of xi, this is a coordinate function on the surface, it's equal to the mean curvature, because the Laplacian of all the coordinates is the mean curvature, dot ei, and that's equal to minus e3 perp dot ei. Here I've used the equation for translation. That's equal to e3 dot ei minus E3 tangent EI. E3 dot EI when I equals 1 or 2, that's 0. So we're doing I equal 1, 2. So this equals minus E3 perp EI. And if you think of that, it doesn't matter where the perp goes. This is just the gradient of xi dot E3. Did I do that right? It's E3 tangent. I got the sign wrong? Okay? Okay, so that says these functions satisfy the operator Laplacian of f minus gradient of f E3. This is the so-called drift Laplacian, familiar to almost everybody in the room except me up to 6 months ago. But it makes sense when you see that for minimal surfaces, the ones you want to look at that correspond to translators, this is the operator you should use. So we're going to try to use this operator on V. So I'm going to accelerate a little. And sorry, so the drift Laplacian of V equals V h squared plus 2 gradient of V squared over V. If you take the drift Laplacian of V eta, you can work that out in terms of the drift Laplacian of V times eta plus the drift Laplacian of eta times V and then you have an inner product of a gradient term. If you're at a point where the gradient of A to V equals 0, that's the gradient of eta V plus V gradient of eta. When this is 0, you can substitute for the gradient of when this is 0, you get an expression for the gradient of eta in terms of the gradient of V. When you substitute that in for this term, you get out that the Laplacian of A to V, that's equal to the drift Laplacian at a critical point, because the drift term is gone, equals eta times V times the norm of A squared. So when eta is positive, V is always positive. This is, we're dealing with a case where we have a surface that's not, that doesn't have absolutely 0 fundamental form. You get that this is greater than or equal to 0. So there's no maximum. Let me do one thing to finish this up. I don't know whether this is coming across at all. I'm in a situation where I want to look at what happens when I take a surface and slide it along horizontally. I'm worried that when I do that, the limit surface, which does exist, is defined over a thinner slab. What I'd like to do is take a line here, which is, let's call the side B, and the side B minus epsilon. I'd like to get a gradient bound on this line. If I have a gradient bound on this line, on the entire line, then when I slide it back, there'll be an upper bound on the gradient of the function u defined here. And I know that this thing is not becoming vertical. The way it's done is like this. So I'm going to try to skip a lot of the details. I'm going to take a region above the x-axis, this region. I have symmetry here, so if I get a gradient bound on a line like this, I have a gradient bound down here. I can do the same thing the other way. What I'm going to do is, if I take this as b minus epsilon, I'll come down just a little bit, b minus 2 epsilon, and take this line, and then take a very, very large value L. Then I'm going to look at the function eta equal 1 minus y over b minus epsilon minus b minus y minus x over L. That function is positive here. So let me now get rid of everything else. In this region, eta is positive. I'll pick some fixed x value. I'll call it x bar. And I'll go down to b minus 2 epsilon and take it till I hit this point here at value x bar. if I look at eta in here, that's positive. So if I want to see where the maximum value of the function, this is v, times eta is, it's going to be taken on the boundary. On this boundary, eta is 0. On this boundary, I take the bound that I get from b minus epsilon. So that's bounded there. Eta itself is bounded there. And along here, I know that asymptotically this becomes a Grim Reaper. This is the axis. So in the Grim Reaper, this becomes a tilted Grim Reaper. So I have a gradient bound along there. So I know that I have bounds here and here. So I have a bound on the maximum value in the interior. Therefore, I have a bound on this. I have a bound on eta times 1 plus grad u squared. Eta here is fixed. So I have some constant gotten by taking the bounds on here plus the bounds here is greater than or equal to eta times v. If I divide by eta and then come in, I see since I'm below here, this thing might get small, but it doesn't get to 0. So along this curve, inside of this large right triangle, I have a bound. Now for this function, I can do this for any L. I let L go to infinity, and I get a bound on the entire line. As L goes to infinity, this line gets more and more horizontal. So on any line below B, I have a gradient bound of u. And that means the band doesn't shrink. Yeah?
On the x-axis, where do you get the gradient bound from that? Because you said you get it because you have tilted Grim Reaper, but this is just, you have just picked one sequence before, where you then see a tilted Grim Reaper.
I think.
That the size is uniform independent of the sequence you go out.
Oh, I get let's see, so I do it, I get one Grim Reaper. That means the farther and farther out I go, the more.
But this depends on the sequence you're taking.
So I need unicity for that limit, huh?
I just was wondering how to get the unicity.
I think it's a good time to stop. The question that Felix asked me, it looks like on that bottom line you have to have an independent bound, but you can prove that that curve is convex downward. So if you have one tilted Grim Reaper asymptotic to it, you know that all the others are going to be the same, and that gives you a specific bound. Okay, so what I want to do is tell you a little bit about, and I'm going to make it a little because this is taking longer than I thought anybody would have known that, how Sprook-Joule convexity is proved. You're starting out with a surface where H equals K1 plus K2 is assumed to be positive. Okay, and we'll make K1 greater than K2. We're going to look at this function H over K1, which is expressed somewhere. It's 1 plus K1 over K2. So in order to show the curvature is positive, since H is positive and the sum of these curvatures and K1 is bigger than K2, this is equivalent to showing that K1 is never negative. And that's the same as showing that the product, the curvature, K equals K1 times K2 is positive. So what you want to show that eta, that this function H over K1 is equal to or greater than 1. Okay. So here is the PDE satisfied by that quantity. So I have to tell you what Q is. H2 is H112 squared plus H22 1 squared. It's a non-negative function where the covariant derivative in the VI direction of Vj, Vk is Hjki. What are the VIs? So the V1, Vi is unit eigenvector in direction for Ki. So I'll assume I have diagonalized the matrix. And I'm also going to assume that these are well defined. In other words, that K1 is strictly bigger than K2. This is an assumption that might be problematic at the end. The first thing I'm going to show is that assuming we have failure, eta, which equals the infimum of this quantity 1 plus K1 over K2, is, well, that quantity is always positive. Assuming that it's in there, it can't be assumed. On the surface. Okay. Okay. If it is, so we'll go by contradiction, we're satisfying that equation. If the minimum is assumed there, then h over K1 is constant. So if I look at that equation, I'm going to get 0, that's the drift Laplacian, equals minus 2h q squared over K1 minus K2 K1 squared. We're at well, it's constant, so this is 0. H is positive, K1 is bigger than K2, K1 is bigger than 0. So this can happen only if and only if Q equals 0, identically equal to 0. So that says that H112 equals H221 equals 0. And by the Cauchy equations, that says H121 equals H122. These are all always 0, 2. Using this, you can show that these vectors, V1 and V2, are parallel on the surface. The parallel on the surface, you get the curvature is identically 0. K1 is positive, so that says K2 is identically 0. And that says that eta equals 1. Remember, eta is just this minimum. This is 0. K2 can't be 0, so K1 is 0. But we're assuming that eta is strictly less than 1. That's a contradiction. Okay, so what are you going to do? You did your best shot with this equation. You know, you find a minimum. You don't get anything. You use what I think is now probably gone in my computer. Use the Omari-Yau maximum principle. So Suppose M is a complete Riemannian manifold with Ricci curvature bounded below, and there's a smooth function that is also bounded below. Then you can find a sequence of points. Now, if the minimum, if the minimum is assumed, sure, you can find this. But this says if it's not assumed, which we now know, you can find a divergent sequence going to the infimum, this function we're looking at. Its gradient goes to 0, and the lim-inf of the Laplacian is non-negative. You then take this sequence and pull back the surface, this graph, by those points. And in the limit, you get something, and I'm going to skip the argument, you get something where it can't be a graph. So the limit has to be a vertical plane. And that means you know that E3 is tangent to the surface there. You then go back and argue really hard with that fact to show that that's a contradiction. I'm going to skip that part. But I find this, I'm not an analyst, I'm sorry, I'm sort of exposing myself. I found this intensely clever and completely not obvious. Why it works, I do not know. One thing that it says here, this is a smooth function. I assume K1 is greater than K2. How can I assume that? There might be umbilic points. But when K1 equals K2, this is 2, so it's never going to come up here. So you can take this function and smooth it out by something that's 1 near the minimum value and is 0 and comes down quickly to 0. And you do it for that function. You compose with such a function, and you can apply this. So the place where this function is not smooth and maybe not even be defined, it won't matter. Okay. I want to talk about the existence of delta wings. I feel a little more comfortable now. My PDE trials are over. I hope. Okay. So, I'm going to take some box in the plane. Base L, length L, and the height, well, let me do it this way. Put the box here, make this minus L plus L, and then minus B plus B. And I want to solve for U. I'll call this domain BL. I want to take domain BL into the reals. I want it to be U equals 0 on the boundary. Okay, so I say this is a minimal surface. I can do it. It's not a minimal surface in Euclidean space. How do I know I can do it? Let me just wave my hands a little, say I'll do it by the method of continuity. I'll look at the metric e to the minus lambda E3 times Dij. Lambda equals 0. This is the Euclidean metric. I know I can solve that. It's a plateau problem, this boundary. And now by the method of continuity, I want to get it up to lambda equals 1. I'm now waving my hands. So I can get a solution for each B and each L. Okay. The translations of that solution foliate. So this is going to be a unique solution. It can't, there's no solution that comes outside because I can move a vertical plane and touch it, should there be a solution that's not graphical. So there's a unique graphical solution, and unique among all possibilities, for this minimal surface in that metric. So there's a unique translator that looks like this. By using Alexandrov moving planes, and remember, vertical planes are minimal, and reflection in them is an isometry of this metric, you can show that the solution has the symmetries of the box. That means that means here the tangent plane is 0, is horizontal, and also I'll skip the proof. if I take x not equal to 0, then x times du dx is positive. If I take y not equal to 0, then y times du dy is also positive. So basically, it comes up here and then down here, up here and then down there. So it looks just like you would expect. It's C1 up to the boundary, except at the corners. This comes from it being a minimal surface. I don't even know whether we're going to need that. And I might need some other stuff about how it behaves along the boundary, how the gradient of this thing behaves along the boundary. I'm going to not prove it. I'm going to just assume it when and if I need it. Okay. So let's say I have a situation where I have an interval across R. It's a situation I'm in. And I have a function u going to reals that's bounded graphical translator. So I'm looking at a situation like this with u equal to 0 on the boundary. I claim that by doing a translation argument, for example, if I take a translation of this, it is also going to be a solution. I claim it's not hard to show that in fact u of xy is in fact u of x. In other words, this is a product surface. I just slide it along. I still get a solution, and then I can show that in fact this is a piece of a graphical of one of the. This is a slice of the Grim Reaper. Let me show you what I mean. I'm not going to show you what I mean. I'm just going to assume that that's true. What it's going to look like, if you think of the Grim Reaper graph, so it's going down here, it says with pi, I can come down with a horizontal plane and slice it. I get a surface on a strip of width less than pi. The width of the Grim Reaper strip is pi, and it has 0 boundary values. So you can make that comparison. I want to take, now I have minus b plus b minus l plus l, and I'll take my, so this is the domain BL. By what I wrote down there, the maximum value is assumed at 0, 0. So suppose I take, for this function, this solution, suppose I take the limit as L goes to infinity of ULB. For some take the limit. Okay. So I just let L get longer and longer. If U star of B is finite, then subsequently you get convergence over a strip. If that's finite, I'm going up, it's going up. I still have 0 boundary values here. This is going out to infinity. I have something that's defined over a strip with 0 boundary values. It must be the slice of the Grim Reaper, and therefore this width of the limit, you get this 2b, you get 2b has to be less than pi. So if I have a strip that's too narrow, that's precisely when this doesn't go to infinity. If I'm in a situation where the width is bigger than pi, so if 2b is greater than pi, ub star goes to infinity. So the center of this graph is getting infinitely high. So I'll take ub xy UBL minus UBL 0, 0. So what I do is at each stage for some subsequence of L's, and I choose them so that this thing is going to converge, I bring it down so that the height is at 0. That means since this height is going to infinity, on the boundary it's going to minus infinity. So I get something defined over a strip. This width is bigger than pi. That's minus infinity here, and 0 here. Well, when you have that width, you also have the symmetries inherited from that box. So not only does it have these symmetry on this line, which is expected, but it has a symmetry on this line. So it can't be a tilted Grim Reaper. Tilted Grim Reaper, when you slice it with the vertical plane, does not have that symmetry. And then you can show that you get a new example on any width, the width pi. It is a graph that basically looks like, not like that. It looks like that. And you can show easily that it's strictly convex. As I pointed out before, you get 1 for each width bigger than pi. When the width goes down to pi, you get basically something that's not tilted, so it's a Grim Reaper. When it goes farther and farther out, you get the bowl soliton. Uniqueness I'm going to skip because there's something that I'd like to really tell you. So we get this picture. So this is the classification, sort of a stumble through it. And now I want to tell you about another way to use what we've found to find new examples that are not graphs, but they're made up of graphs. So let me give you a little prelude. We're going to construct a surface like this that's a translator. Let me take. Okay, so let's take a width W and a length L. And we're going to try to put boundary values plus H minus H, sorry, plus H minus H minus H. So the boundary we expect is going to look like what I just had before. Okay. Now, if I choose L really small, I get a boundary that looks like this. And that will say this is height H. So, sorry, I didn't draw that right. I'm going to make L really, really small. The surface is going to look like this. So the solution you're going to get will have the symmetries of the boundary, but the value here will be approximately H for that curve. Now this is L small. Now I'm going to make L really, really big. Okay. Now, as L goes to infinity, this thing is going to look like something with 0 boundary values. And again, it's going to look like, sorry, I'll translate it up. It's going to look like, if I translate up, something with 0 boundary values. So the value of H here is going to look something like, if I have this width, and I let the width be less than pi, it's going to look like it's going to look like the top slice of a Grim Reaper. Remember that the Grim Reaper looks like this. It is a cylinder. So if I have a width less than pi, I'm going to see something that's about like this with 0 boundary values across the x-axis. So that means that as I make L really, really big, H will be the height at the center will be for small values. The height here of the surface will be approximately log cosine W over 2. Okay. So if I choose now a family going between very, very large and very, very small, provided H is big enough, if H is bigger than this, I can find something where the value here is precisely H over 2. So that means I choose some L of H where I have that picture. And I translate it down to the saddle is at the origin. Okay. So now I let H go to infinity, and I ask what happens. Let me see if I can say it without writing it. Remember, the width is less than pi. If I do this and let this go farther and farther and farther and farther out, if L of H goes to infinity with H, then I get something defined over a strip. And H is getting very, very big, so this is becoming complete, both up and down. L is getting very, very big. I'm assuming that. I get something that's a complete graphical translator defined over a strip whose width is less than pi. By the previous torture I've subjected you to, there is no example. So what you now know is that you can choose a subsequence where h goes to infinity and L of h is bounded. Goes to L. L of h goes to L star. This is of W. Okay, so I now have a picture like that, but now my boundary values are like this. Minus infinity, plus infinity, plus infinity. And that means over these corners, there are vertical lines. Vertical lines are geodesics. You can rotate around vertical lines. That's an isometry. So you can extend this thing to be logged in. You can extend it to get a doubly periodic surface. That's a complete non-graphical translator. Okay, I'm going to put down here a box. This is going to measure W, and W is going to go from 0 to pi. And alpha is going to go from pi over 2 to 0. So a point here is some width W less than pi, and some angle alpha between pi over 2 and 0. So that's my parameter domain. The first thing I'm going to do is we have one of these things for every width. Now, instead of doing that problem, I'll take the width here to be some W, and I'll take this angle to be something less than pi over 2. I'm going to do the same thing. I claim I can do the same thing. Now that has an analog in minimal surfaces. And here's the analog. So that's a perturbed Shor's doubly periodic surface. I want you to look along here. Just look along this line. There's a line on the surface here. What do you see? You see a helicoid. Do you see it, or you just know the right answer? Let me ask you this. This is a minimal surface question. I take a strip. I don't particularly care about its width. And I take 2 points on here, and I want to solve this boundary. So what minimal surface has those boundaries? Everybody knows the answer. A helicoid. It's a helicoid looked at along one of its generators. Take this to be the vertical line, and then go up to the next one. Comes up. You see precisely that picture. So look at from the side. If you pick those lines as being vertical, you get a picture like this. You get these boundary values, and this is the axis. Okay. Okay. So what am I going to try to do here? So I'm going to ask what happens when alpha goes to 0. Okay, when alpha goes to 0, you should expect to see something like this, with boundary values plus infinity, minus infinity, minus infinity. But in order to see this, it has to be that this length is bounded. So I'm going to skip a little. You can make an argument that that length is bounded. So you take this limit as alpha goes to 0, this spreads and spreads out. You can argue that this x of w is bounded. So if you, for example, fix the point in the middle, in the limit you'll see both lines. It's not a hard argument, but I don't have that much time. And so on the surface there might be some, it's not a line, it's some curve on the surface maybe at level 0. But you have a picture like this. And when you extend it by rotation about these lines, you'll get another line up here. That's what happens. So when I rotate, you get minus infinity, plus infinity. And you're going to see a developing helicoid. It is just like a helicoid in its nature. The critical thing is that when you take this limit, two things have to happen. This distance between the vertical lines does not go to infinity. That's not hard to show with a barrier argument. And you get this for any width less than pi. So on this box, we have in here Shirk translators. And they're two periodic. We have over here, when alpha goes to 0, we have helicoidal translators. Anybody want to guess what happens if we go up to this line when the width is pi? But for minimal surfaces, there's no analog. But you do get something. So let me try to show you what happens. So you're going to width pi. And now at each stage, your alpha is really, the width is pi, going to pi. And the question is, what happens to, lost my place. Bingo. Sorry, give me a second. You can try to think what happens. What happens as you go to pi, if you fix So I'm doing this right. Alpha. We're going to fix alpha. We're going to fix alpha and put a pi. So the situation is we have alpha fixed plus infinity here, minus infinity here, minus infinity here. If you come over here to a unit 1 away, and now L is getting bigger and bigger, you can show that first L does have to go to infinity as W goes to pi. Otherwise, you get a contradiction. You get something that's not the Grim Reaper. That's all you can see. And you get something with non-vertical slope here. So you do get something that has the same width. You don't have to worry about that because these lines will be here. So what you see is that as W goes to pi, L of W goes to infinity. So one gets a picture like this. There are now still two lines on it, and you can rotate. So what does the surface look like? It looks like something that's like a Grim Reaper coming in and then becoming extremely vertical here. And you can extend this by rotation about these lines. So the next stage would look like this. Minus infinity, plus infinity. It's a complete surface that is singly periodic. And my gosh, not only do I not have a picture, I don't have a blackboard. What you're going to see is something like this. Imagine one of these flat ends going up, just one. That's the plus infinity. That's propagating along this line. And then along here, imagine these tubes, which are saddles, stretching out ad infinitum. So you get one Grim Reaper-like tube here, one Grim Reaper-like tube there, another one there, ad infinitum. So it's like a blade came down and it chopped miraculously, leaving half a Grim Reaper on one side and then on the other side. And it's singly periodic. Here it looks like it's going to be a plane. And along each of these ends, it looks like it's asymptotic to a Grim Reaper. So this is singly periodic. That angle is alpha. And that's up here. Some arguments have to be made that this limits exist. You don't have to worry about it getting narrower because at each stage you have two lines. The final thing I want to ask you is what happens next? That's this point where they're both going to 0. Sorry, alpha is going to 0 and the width is going to pi. This was a really big surprise. So as alpha goes to 0, you're going to see, you hope, something like this. It gets longer and longer. And here, what just happened? Did I lose it? As alpha goes to 0, this point is going away. So it's minus infinity down here and plus infinity here. Okay, you have to make an argument that shows that this thing doesn't collapse, because now in the limit you have just one line on the boundary. You don't have a line here and a line here. That's a relatively easy argument to make. You have to do some translating to make sure that you don't, like on the Grim Reaper, well, if you pull back the Grim Reaper and you pick the wrong point, you're just going to get two planes. You have to pull it back by the right points to always see the Grim Reaper. You pull back the right points and you get a solution like this. This width is pi. Alpha is going to 0. And there's one line on it. So this is not a periodic surface. You can rotate once, and then you get up here, well, sorry. So this is plus infinity on this side and minus infinity on this side. When I rotate, I get minus infinity on this side, plus infinity on this side, and minus infinity here. So this is a complete translator with one line on it, asymptotic going this way to a Grim Reaper, going down. Here, asymptotic to a Grim Reaper up here. And in the other quadrants, I go from plus infinity to minus infinity. So here, I see things diverging. It's So this is graphical over this entire strip minus this line, when you throw in this line which connects the two sides. So there's no minimal surface analog, but it's a natural limit of minimal surface like translators, and it's so unusual that we gave it a name. We're calling it Jack the Reaper. It's simple enough that maybe it's a model for singularity formation. I don't know of any other analogs like this, and this was completely unexpected. So I'm leaving out because it seems like a form of sadistic torture to tell you all the little steps you have to make to say that these limits exist. But there's this picture now. There's a two-parameter family that extends to the boundary. Oh, what happens here? Well, when you let W go to 0 and you rescale, you get what you expect. You'd get Shirk surfaces and helicoids. You do have to rescale. So everything is nice along here. So it's like the classical family of Shirk surfaces and helicoids propagate out. They're reasonable in here. They're Shirk translators. Over here, they're helicoidal. On top, they're strange. They're like planes coming into a family of Grim Reapers. Oh, and then when they come together, you get something bizarre like that. I'm going to stop. Thank you for listening.